Alright guys, so today we're going to talk about precipitates and precipitation reaction. Now, this is our dot point down here, obviously. We're going to identify some combinations of solutions, and we're also going to do this with an experiment in class next lesson. Alright, so what's the point? Basically, you want to be able to explain what a precipitate is, which we see happening here in a fairly dramatic reaction. And that's why these are fun, because they are fairly dramatic. We want to describe what is happening in terms of the ions involved when a precipitate occurs. We want to be able to use a net ionic equation to explain what's happening in a precipitation reaction. And finally, we want to be able to predict outcomes using the solubility rules that we'll talk about right at the end. Alright, so when we add two soluble ionic compounds together in solutions and we mix them together, there are two possibilities. Now, generally we look at what is called a substitution reaction. The first is that the solutions simply mix together, but the second is that a solid called a precipitate comes out of the water, so forms in the water and it becomes a solid. Alright, so a precipitate is an ionic compound that is insoluble in water and forms as a solid from reactions between two soluble ionic solutions. Okay, so let's look at an example. Let's look at potassium iodide added to lead nitrate. Now it's very important that you see, hang on, let's go you see this here, and you notice that that and that, they are aqueous, which means it doesn't actually exist as this. It exists as the two ions for each one in solution, so just disassociated out. Alrighty, so potassium iodide and lead nitrate. They're both soluble ionic compounds. So we mix them together, we get a yellow precipitate of lead iodide, and we see that right here. And it's really dramatic. These two clear solutions, we put them together, and there's the big chunky yellow mess. So a substitution reaction occurs, which is the AB plus CD gives you AD plus CB. That's the standard format. So we have lead ions and iodide ions. So the lead is the positive and this one is the negative ions. They, from their separate solutions, they join together and they form lead iodide. Now, this means that these two are attracted together so strongly that they form a crystal lattice. Now, remember, the water breaks apart those bonds, and they're so attracted that the water can't do that. And you get the crystal lattice inside the solution, inside the water. So therefore, they're insoluble. Now, let's look at the symbol equation for this. So you have two potassium iodides, aqueous, plus one lead nitrate, aqueous, gives you two potassium nitrates, aqueous, plus one lead iodide, solid. Okay, so we want to do an ionic equations, which basically shows the movement of the ions and how they change. So the symbol equation is as before. Now, if we take out these ones, so there's the potassium's gone, and potassium's gone over here. The nitrate's gone, and the nitrate's gone over here. Because as we said, these ones are dissociated out, this one's dissociated out, and here they're dissociated together. This means these ones are taken out because they're spectator ions. So as nothing actually happens, they stay unchanged, they stay disassociated in the solution. If we evaporated the water, sure, they would crystallize, but as they are separated out, they're disassociated, okay? So they are spectator ions, and they take no part in the reaction at all. So the ionic equation looks like this. We get Pb, 2 plus, remember it's aqueous, plus iodine, plus, or iodide, minus, also aqueous, and then it's the solid. That's the change. Alrighty. We always assume that the precipitation reaction goes to completion. It won't always, not in real life, but for us, it makes sense to work as though it does. Here are our solubility rules. So basically, we can predict the precipitation reaction using the solubility rules. Alright? So these are the things which we call soluble. All nitrates, all acetates, all of the chlorides and iodides, except for mercury chloride, lead chloride, and silver chloride. All ammonium compounds, and all sodium and potassium compounds. You can see these working over here. So the insoluble ones, any carbonate is insoluble, except for sodium, potassium, and ammonium. All of the oxides and hydroxides are insoluble, except for sodium, potassium, calcium, magnesium, and barium. And I would imagine, yeah, all sulfides are insoluble, except for, again, the same crew of insoluble ones, and all phosphates. Oh, sorry, all soluble ones, and all the phosphates are insoluble, except for sodium, potassium, and ammonium. All right, now, when we say solubility, or something soluble, what we're saying is if you can easily dissolve to 0.1 mole per liter, that's soluble. If something's less than 0.0001, or 10 to the minus 4 moles per liter, we say it's insoluble. And then we can say stuff in between is slightly soluble, almost soluble, etc. All right, that's it. I hope that all makes sense, and we'll see you in class, and we'll make some precipitation.